Why all of a sudden is it doing that?
It wants to talk to you.
Must be some new thing that Zoom people have added in here, because I wasn't doing that prior to today, but we are here, Algebra 1A, beginning of week 8. And we're going to be wrapping up the 3rd unit this week, which involves inequalities now and systems of inequalities. So the inequality work that we've done previously was only on a single number line and only involving one variable. Now we're talking about inequalities that are going to be graphed on the XY coordinate plane. So now we're talking about inequalities in 2 variables. So it's not just a single number line graph anymore. So hopefully this won't be too confusing. But we've got another week after this week. The Unit 3 test will get released the end of this week once we finish this material. And then next week I'll be available during class time to answer questions or provide extra help, but there won't be formal instruction. So the final is next week. I will have materials printed out for practice to prepare for the final. My suggestion on that preparation sheet is to concentrate on the items that you don't understand or that you're struggling with. It's not going to be graded. You're not going to turn it in. It really is a guide for you to understand what might be on the final. And please don't anybody panic about the final. It's 10 questions. It's 50 points. So final is not going to make or break your grade in this class. It might put you over from one grade level to the next grade level. If you're like at a BC borderline, it might put you over the top. So it can help you with that because it's only 10% of your grade. These 3 unit tests, the 3rd one being later this week, those are 80% of your grade. So you can do those twice, but the final you can only do once. Anybody have questions about any of that so far? All right. So linear inequalities. Well, we're still talking about straight lines. The other day I mentioned this idea about having a half plane on our graph and what we're talking about as a boundary line. These type of inequalities, x is greater than 20 or x is less than 20, that's a single variable inequality. You can do those on a single number line, traditional horizontal number line. Not complex at all. Linear inequality, though, gets into equations that look like slope-intercept. In other words, y equals mx plus b. The only difference being instead of an equal sign, now you're going to have an inequality symbol, less than or greater than, less than or equal to, or greater than or equal to. So one of those 4 symbols is going to be part of our linear inequalities now in this lesson. The very bottom there are some examples. Actually, this whole screen is about examples. You don't get into linear inequalities with any of those first 4. Those are all equations. And one thing you really have to be careful of is using an equal sign when it's an inequality, because it's not the same thing. You have to really watch those signs carefully. So the ones that we're going to be working with are more like this one: y is less than or equal to 2x plus 5, or negative x plus y equals 6, or 2y is greater than x. But this one in the middle here, this negative x plus y equals 6, that is not an inequality. That's just an equation. We're not going to see many of those. Last Thursday, we talked about how finding solutions is now a little different, because now we're not talking about the points on a line necessarily. In both of these examples here, you've got an ordered pair, and it's asking, is it a solution of an inequality? When we were finding solutions with equations, we could take an ordered pair and plug them in and get an answer to that. We could do the same thing with inequalities. This -2 is our x value, -3 is the y value, so substitute them in. So if I put -3 here for y and -2 here for x, I get -2 times -2, which is +4, plus 1 is -3 less than 5. Yeah, sure is. It's less than 5, so that point is one possible solution. Do the same thing with the next one. Now I have an ordered pair of 1, -1, y less than -2, x plus 1. So y is -1, x is 1. So -2 times 1 is -2, plus 1 is -1. So -1 less than -1. Not a solution, right? Not a solution because it's equal to it. We have to be very precise about how we interpret these. And you can see when you plot these points on a graph, which ones are solutions and which ones are not. -2, -3, left 2, down 3. That's right, square in the middle of that colored in area. This is that half plane in the vocabulary, the half of the graph that is part of the solution. The other point, 1, -1, we go 1 to the right and down 1, is actually right on the dotted line. The dotted line is the boundary, but it's not part of the solution. It is not included. Because our graph here, our equation, and the graph it represents is for less than. And this is the big change about these kind of problems that you have to get used to. Now we're talking about the style of a line that you have to deal with. Dash line or solid line. Solid line is going to include the equal to amounts. So in this last one, if this had been a solid line, we could have accepted 1, -1 as a solution because it would have been right on the solid line. Well, when it's less than or greater than, and you have to graph it with a dashed line, that's the boundary of the solution area, but it's not included. So anything that's on that dashed line is not going to be a solution. Then once you start graphing these, you also have to put that colored shading on here or draw lines on it or somehow designate what the half plane is that's part of that represents the solution area. Because now we're not talking about a single number that's a solution. We're talking about a whole area of a graph that includes every point under the shaded area. Questions, anybody? So y less than x minus 3. Dashed line or solid line? Yeah, good. Right, right. X minus 3. Our y-intercept is here. +1 slope in this direction. I'm going to change that style. There we go. There's my dashed line. That's my boundary line. So a lot of people will have trouble figuring out where to put the shading now, because just graphing a line like that is not enough anymore. Not for these inequalities. Because we need all the values for y that are going to end up less than x minus 3. So if I go to the y-intercept of -3, and I go down, all of that area below the line is going to represent the solution area. So if I'm doing this on a sheet of paper, I didn't mean to do that. Sorry. There we go. All this area below my dashed line everything below that dashed line is part of my solution. It's simpler for me to just to do this sort of big block area on this PowerPoint than to try to draw a bunch of lines. But later on, when we start doing systems of inequalities, we'll have 2 of these areas. Then we'll be looking for the part that overlaps. Everybody okay so far with these? I'll change that wording. So you've probably seen a variation of this inequality before, very similar to some equations that we've had. Solid line or dashed line? Yep, solid line, and it's going to be going up to the left. Hopefully you recognize just from the way I'm talking about it, my thought process on this. Before I even draw anything, I'd like to have a grasp of the shape that I'm going to be putting on here. Is it a solid line or dashed line? So that's the first thing I think of. My y-intercept is down here at, let me put a circle on that spot, -5. That's always our starting point. Right, there's the y-intercept. Now let's get our boundary line put in there. Less than or equal to -9/4. So I got to go up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And to the left 4. 1, 2, 3, 4. Can't go the other direction. Because what happens if I go the other direction with my line? The big thing is what you said at first, that it makes it, the line would be going in a positive direction. So that's the second thing I try to visualize when I'm thinking about a graph like this is, I know in my mind's eye that this any negative sloped graph is going to go up to the left. So if I put a point over here in this first quadrant, it's not going to go the correct direction. It's going to go in a positive direction, and I'm not going to understand how I'm even wrong perhaps, because now I'm thinking which one of these is negative and which one's positive. Well, it doesn't matter. Remember, when we have mixed signs on our slope, one of them's positive, the other one's negative. So if I'm down here at -5, I've gone up 9. Well, that's +9, right? When I go up on the graph, I'm moving in a positive direction. If I go right, now that's positive again. So that would not be a negative slope anyway, because now I got two positive movements, positive rise, positive run. No way it can be negative. So once I go up 9, I have to go left 4, because left is negative. Now I got my signs mixed, and I know that the line's going to be going graphed in the correct direction. Similar to the last one, less than or equal to, above or below? Below, right. Below the line. So any point that I would put in this green area, however large I make it, any point I put in that green area is going to be considered a solution. Even points that are off the graph, those still would be part of the solution.
Well, if it happens, the equality sign, whatever falls on the line would be part of the solution as well, correct?
Jessica just brought up a good point. If we had a point that was actually right on the line, it would still be part of the solution. And that's what the solid line tells us. And that's why we got to think about that when we graph these, because it's a significant difference between the simple less than or greater than and these that also include that equal to symbol underneath the inequality symbol. Now, if we're on the line here, it is part of the solution. Question, anybody? Okay, thank you. Now, people in class here actually have a little bit of an advantage over you guys at home, because I just handed them a paper copy of this. This was the handout that I was waiting for to come off the printer earlier. And it's just like those examples that were in the slideshow. Numbers may be a little different. But it still works. It's a little tougher to do it in Google Classroom. In fact, I haven't even quite figured out how to do it. But if you get a chance, and you can print this out, or if you come in and want to get a hard copy. Wait a minute. So I almost forgot that I had done a Jamboard for this, these same problems. So I went ahead and I've got that opened up here. I've shared it out with everybody. So this could be another option for you at home if you want to take notes. So here's the first problem that was in the handout. Y less than or equal to 8/3x minus 3. Well, here's my y-intercept at -3. I'm going to need a solid line because of that symbol there with the equal to sign. It's got a positive slope, and I know all positive slope lines go in that direction. So I'm going to go up 8. 1, 2, 3, 4, 5, 6, 7, 8, and over 3. 1, 2, 3. In solid line. Less than or equal to is going to be going in this direction. And this is those lines going from left to right there. That's usually how I show shading. You don't have to color it all in. You know, whatever makes the most sense to you. The reason I do this directional sort of shading is because when we have to start doing systems of inequalities, now I've got a second shaded area I've got to put on the same graph. So if I have lines going in one direction for one of the graphs, I want to make lines go in the opposite direction, perpendicular, for the second graph, for the second equation or second inequality. That way they cross and give me like a checkerboard that I can clearly identify where the overlap is, because that's what the bottom line is for these systems of inequalities, as you'll see. So here's the second problem on that handout. Y is greater than negative 5x plus 3. Just like always, we're going to start at the y-intercept. That's our beginning point. This is B. B for beginning. Slope is m, number in front of x. Negative slope lines go this direction. That symbol tells me I got to do a dashed line. And I can't really go up 5 and over 1 because I'm off the graph. I'm going to go down 5. 1, 2, 3, 4, 5, and over 1. Well, why did I do 5 over 1? I can take any whole number slope and put it over 1. It doesn't change a thing, but it does help me see the rise and the run. It's not 5, it's not negative 5 over 0, it's negative 5 over 1. So now I can put my dashed line in there. Not very straight, obviously. It's supposed to be straighter than that. Greater than. Now my shading's going the other side of the line, above the line. Now, when I was looking at the other one, I went to the y-intercept and I went down because it was less than. I'm doing the same thing here, only the opposite because it's greater than. I'm going to the y-intercept and I'm going up on the y-axis. I mean, this whole inequality, y depends on x. So no matter what x is, y has to be greater than the combination of all that calculation. That's why I'm going to go from the y-intercept and go up for the solution areas. So how do you know for certain if you've got the shading in the right area? We're going to test.
Test 0, 0.
I like to use 0, 0 anytime I can. So 0, 0 on the way I've graphed it is not in the shaded area. So it should not be a solution. So just like I did on the slideshow, I can substitute 0 for x, the other 0 for y, substitute. So negative 5 times 0 here is going to give me 0. So is 0 greater than 3?
No.
Nope. So that tells me it's not a solution and confirms that I've got the shading in the right area. If I had shaded it on this side and then done that substitution to test it, I would have gotten a no solution mathematically, which should tell me, oh, shading does not go on this side. You can do that with any of these inequalities. 0, 0 is a good one to test because it simplifies your calculations, obviously. And then what you've got is y is in some relationship with your y-intercept. Clearly 0, 0 is not a solution as a result of that. Quick little test. And whoever that was chiming in out there, thank you. You're on it. Questions, anybody? All right, here's the third example. 2x minus 5y less than -5. It's in standard form. Can we graph it? Well, yeah, but we need to know the intercepts. And 2 doesn't go into -5 evenly, so I'm going to end up with a fraction somewhere. I don't want to mess with that. So what do we do when we have a standard form equation? Convert, yes. Convert to y, in this case, less than mx plus b. Convert, convert, convert. And all that really means is solve for y. This goes back to, I think, week 2, basically, when we started looking at these literal equations, these formulas. We can move these terms around any way we want, as long as we use the opposite operations. Here we get the cancellation on the left, and then we can use it on the right. And so then our next step becomes -5y less than -2x minus 5. Okay. Now what?
Divide by -5.
Yep. Divide by -5. There's our coefficient for our y term. And now, because we're dealing with inequalities, we got a special rule to remember.
We have to change the less than to bigger than.
This one?
Yes.
Very good, Esma. That's exactly right.
Because
Remember,
we divide or multiply by negative, we have to change.
perfect. Remember that inequality rule. Actually, divide or multiply. Changes the inequality symbol. Actually, I'm going to say reverse. So that's going to have to be our next, oops. Left out a letter there, divide, multiply by negative, reverse the inequality symbol. Okay, so my next step here, those are going to cancel. So I'll end up with y. Now this has to be reversed and becomes that. -2 over -5 makes those positive. 2 over 5x. -5 divided by -5 is a +1. Okay. Now it's in a format that's much easier to graph. Because it's like every other slope-intercept form equation, go to the y-intercept. I actually kind of like fractions like this because now it's obvious what the rise and the run are. The rise being the top number, the run being the bottom number. So up 2 over 5 to the right, 1, 2, 3, 4, 5. And this symbol now says greater than dash line or solid line.
Dash.
Dash line.
Yep. So now our shading's going to be above. Because if you don't reverse that inequality symbol, there's no way you can ever get a correct answer or get the solution area identified properly. So you can tell just from this one standard form style problem, it's a little bit more complicated. You got more steps to go through than just, plunking a line on the graph from like slope intercept. But that's true of, standard form when it's in a standard form equation. It's better or it's more reliable to convert it anytime you can. Questions, anybody? All right. Okay, similar. Standard form again. Keep saying standard form. In case you don't remember, it's ax plus by. In this case, less than or equal to 6. But I meant to have that all in standard form, so that should be a C. Because that's what standard form is. So what should the converted form be? Okay, that sounds like what it is now, but what's the converted? Once you've converted it over to slope intercept format. Remember, there are a couple of steps here, and it works every time. The first thing you got to do is move or cancel the x term. Because slope intercept is y equals mx plus b. The x term is on the other side of the equal sign. How do we get it to the other side? Well, we have to cancel it on the left. And we're still talking opposite operations. So if we do something and balance, so if we do something on the left, we have to do the same thing on the right. So we subtract x. Right? So that gives us then 2y less than or equal to negative x plus 6. And I always put that x term right after the inequality symbol, because that's where it needs to go in slope intercept form anyway. You don't have to put it at the end. And technically, some people would say that you have to, but I'm just looking at it as a shortcut. I need it to be there in that position anyway, so why not just put it there? So for the second step of this conversion,
Divide by 2.
yes. And I'm going to be a little bit more general than that. We're going to divide by the coefficient of y, because that's what the 2 is. And you're going to do that. And I keep using that term, that phrase, coefficient of y, because I want you guys to really hone in on the fact that this coefficient, that word coefficient, tells you something about the problem. It's not just some fancy word that's thrown in here. We're going to divide by that coefficient because that's the only way we can get to 1y. This is 2 times y. Okay, the reason we divide then is because that's the opposite operation. The thing that's a little bit weird about this problem is I don't see a coefficient in front of the x. Okay, well, no big deal. Just make it -1. It's a single letter, so we know that the coefficient of that term has got to be 1 or -1. The sign tells you it's -1. It's easier just to put that x there so that it shows up, because now, again, this is my slope. I can see both numbers as my rise and run instead of just having -x/2. If you just write -x/2, I'm not sure that's clear enough to know what the slope is and how to work with it. So I would not do that. That's why until you really get good with this stuff, stick the 1 in there so you can see the slope better. So we get y is less than or equal to -1/2 x plus 3. Don't have to, we didn't divide by negative, so I don't have to do anything with the inequality symbol. All we did was convert it. So just like all the others, now that it's in slope intercept, it's the same, again, the same process we've been doing since we started graphing on the XY plane. It's a negative slope. It's going to go that direction, up to the left, up 1/2. Put another point up here, up 1/2. Solid line, less than or equal to is below. Now I got the whole solution area. Now in this case, if you use 0, 0 to test your conclusion, I can use the original equation or I can use my new equation. Why not use the original? Because it doesn't have a fraction in it. Well, this becomes 0 plus 0 less than or equal to 6. That's true. 0 is less than or equal to 6. And that's where I got the shading. The shading goes over the 0, 0 point. So that's the advantage of taking a point like that and testing it. I mean, we could choose any point that we want to on the graph and do that test. Questions? Anybody? Okay, so now we're going to add to this. We're going to start talking about systems of inequalities. So far with systems, we've talked about solving systems by graphing. When it's systems of equations, by graphing, by substitution, and by elimination. Really, the best one for systems of inequalities is going to be graphing. There's just too many possible combinations if you're talking about trying to figure out elimination or substitution with inequalities, because remember with systems of equations, there are only three possibilities. You can have one solution, you can have no solution, or you can have infinite solution. It's not nearly so cut and dried or so simple when you're talking about now a system of inequalities where you have whole areas of the graph involved. We've got the same sort of things with boundary line or shaded regions, like called half planes again. We're looking for points and areas where those half planes intersect, and we can do the same kind of testing. We can take a point, it's inside both, or it's in one or the other, and we can verify that we have shading in the correct area. So now for a system of inequalities, the solution is the overlap. So typically what I would do is I will do one of these at a time. I'll put the shaded area, I'll graph the line, do the shaded area for one inequality. Then I'll graph the line, do the shaded area for the other inequality, and look specifically for where one of those shaded areas lays right on top of the other. If they don't have anything in common, there's no solution. Typically, though, they're going to overlap someplace. So here's an example. Go back to my original here. So the green represents the shading from the first one. Which one of those inequalities is that? Okay, it's got to be this first one because the black line has a negative slope. And the only of these two equations, only that first equation has a negative slope. And I go down here and, well, the line shifted a little bit, but probably because I've been messing with it like this. Move that over. There's my y-intercept at -3. Red line, y-intercept of +3. So a lot going on here with these kind of systems of inequalities. So I got line style on both of these to worry about. Thankfully, they're both solid lines because they both have the equal to symbol. The first one, negative slope, less than or equal to. So my green area, my shaded area has to be below the line. On the second one, greater than or equal to now is going to be above the red line. It's so much easier when you're doing this on a piece of paper, honestly. So all of this area here where the gray overlaps the green is part of the solution. Everything to that side. This little green area down here, this little triangle down here that is just green, that's a solution for one, but it's not a solution for the other, so I don't really care about it. Now, this one over here on the left, that really should be under the gray. If I had it on a piece of paper, it would be obvious. But this area down here, between the red and the black, is only a solution for one of these, so it doesn't count. We don't care about it. All the rest of this area out here to the right, that's like no man's land. That's not a solution for either one of them. And you could still do the same thing here. You could use that 0, 0 point to do your little test. 0, less than or equal to -3 for the first one. Yep, that's true. 0 greater than or equal to 3. Wait a minute, how did I do that? It's not greater than. It's plus 3. Did I do something wrong? Okay. Well, the reason I'm stumbling is because this first one is true. Where is it? 0 less than or equal to -3? No, I'm having brain fade this afternoon. Neither one of these are true. So it can't be part of the solution area. 0, 0. I didn't do that on purpose. That's just the way it worked out. Now, nice clean drawing of this would come up like this. I don't have the ability to put that on here in quite such a clean manner. But it's the same area. The other thing that couldn't really see with my gray and green, I don't know if I can change those or not.
So as you're flipping back and forth between this side and the other side where it's cleaner, as you put it, the other one where the 2 lines at the top, after they cross in the middle, why is that not shaded in between the 2 lines?
It's not shaded in between the 2 lines on this one either, on mine.
Okay, so that shouldn't, okay.
It's in the same way that this green area down here only has one of the shadings. This whole triangle right up here is only gray. There's no green behind this part of this gray one up here where I'm moving this. You know, I was just trying to figure out if I could make this transparent somehow or make it, you know, have a design of some sort so you'd be able to see that. I didn't pick up on that at first, and I'm glad you asked that though, because it is more obvious on this that this is not part of the solution area, and neither is that. Well, on mine, it's easy to see this green area down here by itself is not part of the solution. Right. That's what I'm saying. The green here all by itself matches this clear area right here. The gray area here all by itself matches the clear area here. Remember, we're talking about overlap. It's got to have both colors to be the solution area. And so on this one with just the red, it's only showing this area right here. And let me see, let me put another, this is going to really look messy. But if I draw this line to there, let's make that blue. And I'll do another. Another line here. That's blue also. So only the stuff that is left of those blue lines.
So after the lines cross, you start from there and shade out.
Yeah, and because I'm only looking for the overlap. I need to know the area of the graph where both colors are intersecting. This area up here, this little triangle that's to the right of my blue line and above the red line, that's only got gray in it. So that's a solution to the one that I said was for gray. But it doesn't matter because this is a system. It's got any solutions have to work for both. So any area that's only colored gray or any area that's only colored green don't count, because they include solutions for one but not both. Okay. I don't know if you guys out there got questions on the same thing, but it should be more clear when I go back to this Jamboard. So hang on just 1 second. So you can play with it or work with it on your own if you want to. And so hopefully now, these are on the flip side of the paper I handed out here in the class. It's on the back side of this information, the paper that's in the Google Docs. So it's the same problems. So y greater than or equal to 4x plus 3, y less than or equal to negative x minus 2. So two solid lines. Y-intercept for the first one. If I go up 4, I'm off the graph, so I'll have to reverse everything. 1, 2, 3, 4 over 1. Solid line greater than, it's above. See, this is where I start doing my shading as lines go in different directions. So that's all the shaded area for the first one. The other one, my y-intercept is -2. Also a solid line, -1 slope. So it's going in this direction. And now the only areas that I care about, this is the shaded area. Now, this area over here is still shaded from the second one. This area up here is still shaded from the first one, but they don't overlap. So they're not part of the solution for the system, because that's all I care about. This is my overlap area. You could draw those other lines for the solutions for each individual inequality. And there's nothing wrong with those, but they're not part of the solution for the system because they don't overlap. And last week, I think I was joking about using colored pencils and stuff like that. This is a perfect kind of problem for that. Get your colored pencils out, or your crayons or your markers or whatever. Do one area in one color and do the other one in a different color, and where they overlap is going to be clearly obvious that is your solution area. Okay, now this next example here is a little different because we have one that's an inequality and one that's is less than, and the other one includes the equal to symbol. They're both less than, but one is also less than or equal to. So first one down here at -3, y-intercept up to 1 to the left, up to 1 to the left. This has got to be a dashed line. Less than is going to be below. Okay, the other one, also negative slope, different starting point, y-intercept of +2, up 1 over 3, up 1 over 3 to the left, up 1, 1, 2, 3 to the left. Solid line. Here's what I meant before when I was talking about the sort of the checkerboard pattern. And I'm kind of making it more obvious here. My shaded area for the first one, the dashed line goes down to the left. My dash or the shaded area for the solid line goes down to the right. Where they cross, the boxes that are created, that is the overlap area. Any area that's just got a single set of lines in it is not part of the solution for the system. It is a solution for one of the inequalities. But again, that doesn't matter because we're talking about a system. We got to have solutions that work for both. Questions, anybody? All right, looks like we are going to get through this today because we've only got 2 more problems as kind of our representative examples. And hopefully you can see this is kind of more of the same stuff. You're just doing it again and again and again. And there are some systems problems at some level of algebra where you can have 3 equations or 3 inequalities on a graph. Those can really get confusing. Thankfully, we're not messing with those. So standard form again, do the conversion. All right, we're going to take x away from the first one. Take 4x away from the second one. And rewrite them. (3y) less than or equal to negative x plus 3 for the first one. The other one says 3y less than or equal to negative 4x minus 6. What do we do next? Yep, divide by 3. Everything gets divided by 3 because that's our coefficient. And ironically, it's the coefficient for the y term on both of these. Divide by 3. By 3. Everything gets divided by 3. So y less than or equal to negative 1/3 x plus 1. Y less than or equal to negative 4/3 x minus 2. Now we've done the conversion. This is actually kind of the routine part because if you're comfortable with graphing, this part's easy. Starting at our y-intercept, up 1, 3 to the left, because that's negative. This tells us it's a solid line. Less than or equal to is below. Okay, the other one starts at negative 2. Also negative slope, and now we're going up 4. 1, 2, 3, 4, and over 3. Another solid line. Also less than. So we got some area here with these single lines that was left over from the first one. That's not part of the solution for the system because there's just one set of lines in there. Anybody want to try the last one? That's okay. Anybody want to talk me through it? We do have to convert it again. Not divide. Nope, not yet. We're just canceling. We cancel with opposite signs. Right? Negative 2x cancels positive 2x. X cancels negative x. If all we're doing is moving from one side to the other, we're doing that with just the opposite sign. Negative y less than or equal to negative 2x minus 3. Now that's our next step there. The other one, negative 3y less than or equal to negative x plus 6. Okay, what next and what do we have to watch out for? Say that again, Kathy. Both of these inequalities are going to end up being divided by a negative. So the reason I asked that before I started doing anything is because I want to put that in my mind before I even take the next step. These are both going to end up getting reversed. Because this first one, I'm going to divide by negative 1. All I needed to do was change that sign, so we use negative 1 for that. The second one, now I'm going to divide by that coefficient, which is negative 3. Hard time writing those today. So I already changed the symbol. That becomes 2x positive. This becomes plus 3. The other one, 1/3 x minus 2. So you can tell there's a lot more stuff to remember. And this business about reversing the inequality, that didn't come from this lesson. This came from the previous lessons that we did on just plain old one variable inequalities. We always have to do that reversal whenever we're multiplying or dividing by a negative. So we don't want to forget that. Positive slope, solid line for the first one, up 2/1. Greater than or equal to is above. Other one starts at negative 2, up 1/3. Another solid line also above. So now we're only in this area up here as our solution. A lot more area that's not a solution on that one than there is. Questions, anybody? If you want more problems like these to practice on, I've got plenty of other examples. I have not posted them in Google Classroom, but let me know. you know, the good news, I guess, for this particular unit test, you're not going to have to graph these kind of problems in the test. But you might have to match up the inequalities that you're given with a graph that you're shown. So there might be a graph, and then there might be 4 different sets of pairs of inequalities in a system format. Okay, which one of these sets, which one of these pairs represents that particular graph? So you're going to have to visually be able to connect the dots, so to speak, and recognize which inequalities go with a particular graph that you're being shown. So it's kind of the opposite of what we're doing right now. But if all you saw was this graph, you need to find these inequalities, because that's what has generated that graph. So the good news, I guess, is since we got through all this today, I'll be able to post the preparation guide for the final, and we could start working on that on Thursday. And you'll have a couple extra days to finish the Unit 3 test. No, I didn't want to do that until I figured out how far we could get today. So probably be tomorrow. All right. Okay, guys. Thanks for being here. Thanks for y'all at home or wherever you're at today.
Thank you.
All right.
Thank you.
Talk to you later. Have a good evening.
Thank
Thanks
you
for
too.
being here.